Hi everyone. Today we are going to discuss about the graph traversals. So graph traversal is a technique used for searching the vertex in a graph. So also it used to decide the order verticals to be visited in the search process. The graph traversal finds the search process without creating it. See these graph traversals. Uh, Actually, we have a graph now. Okay. So in that graph, we need to search each vertex. Means suppose A, B, C is a graph is there. So in this ABC graph, we are going to search A vertex, B vertex, and C vertex. So suppose this triangle is in a closed loop, nothing but it is in a loop. Means there is no spanning. There is no spanning tree. So by the aim of this graph traversals is that so what are the loops we have in the graph that are going to be removed means we are going to make this graph in the spanning tree. Okay, so the here we having two types of graph traversals. Those are depth first search and breadth first search. These are the two techniques we are using in the graph traversals. Okay, so first one we'll see that DFS, nothing but depth first search. The aim of this graph traversals is what here to make a spanning tree. The spanning tree is what here? The spanning tree is nothing but the graph without any loops. So here we having loop A, D, E is a loop. So what we have to do? We need to make without loop of this AD and ABE and BCE like that. Means finally what we are doing here. So we are going to make a graph in a spanning tree. The spanning tree is what here? The spanning tree is nothing but the graph without any loops. So for that, what we are doing here, we are going to use the stack data structure. Okay, we are going to use the stack data structure. So what is a stack? Stack which follows the LIFO rule, nothing but last in first out. So here, before start this process, what we have to do, so we need to know that how many vertices we have in the graph. So by using that number of vertices, we are going to declare the size of an array. So here, so A 1, 2, 3, 4, 5, 6, and 7. So seven vertices are there. That's why we are going to make the size of a stack as the 7. Okay. Define a stack size, the total number of vertices in a graph. Okay. Now what is the size of a stack here? The size of a stack is 7. So now which technique we are using? We are using the DFS. Remember, whenever you are using the depth first search, we are going to use the data structure is what here? The data structure is stack. Okay. Let me start the process. The step number 1. Select any vertex as a starting point for traversal. So visit that vertex and push it on the stack. So now select any random vertex means A, maybe you can take D also, no problem. So now I'm choosing that A as a vertex. Okay, starting point of a vertex. Now what is the ending point of a vertex? I'm choosing that G is the ending point of a vertex. So first, whatever you visited, so now you taking the point as a starting point as an A now. So now what will happen? You are visited this node. Nothing but this vertices is visited. So when you are visited, then what we have to do? We need to push this vertex A into the stack. So what you observe here? Whenever you visited a new node, whenever you visited a new node, that new node you need to push into where into the stack. Okay, next we will see. So step number that is the step number 1. Now we move to the step number 2. So visit any graph of one of the adjacent vertex of the vertex which at top of the stack which is not visited and push into the stack. See here in these In this, what happened? We visited A. So from here you can visit B, you can visit E, you can visit D also. So whatever you visited, that you need to push into the stack. Now what happened? Now I visited the adjacent of A. Which one? We're having B here. We also having E. But what I chose here, I chose the B vertex of the next visited. So B is not visited. Then what will happen? Now we are visiting. So whenever you visit a newly visited node, what have to do here? We need to push into the stack. So where you have to store the data? The top of the stack. Already we know that the operations are done in the stack by using the top. Means so push operation is done on the top and pop operation is going to be done on the top. Now, so after visiting this B, next what are the adjacent vertices we having here? Next one is C, another one is the E. Okay, now choose any one, either C or E. So now in step number 3, repeat step 3 until there are no new vertex to be visited from the top of the stack. On top of the stack. Say visit any adjacent vertex of B. So C is not visited now. Then what happened? Now I'm going to visit the C. So C is not visited. Now I'm visiting. Then what will happen? Then when you are visited new node, then again what we have to do? We need to push it to the stack. Now the what is the top of the stack we having here? Top of the stack is we having C. Then next come into the step number 4. So what are the adjacent of the C here? C we having adjacent E is there, F is there, G is there. So you can choose any one. So I'm which is not visited. You can choose. Now E is not visited. Then what I'm doing here? I'm going to visit the E. So E is not visited now. Then so which is adjacent of C. Now I'm going to visit it here. We are going to visit here. Then what will happen whenever you're visiting the new node? Then what have to do here? We need to push into the stack. So, right now, so move to the step number 5. So step number 5. What is the step number 5 here? Visit adjacent vertex E, which is not visited T. Yes or no? So here the what is the adjacent element of E here? D we having and F we having. So both are not visited. Now I am choosing the D here. Okay, now I am choosing the D. So right in step number 5, what will happen? Now I'm choosing the D. So now D is visited. Before that is not visited now. So then what will happen? We need to push into where? We need to push into the stack. Now D is the top up on the stack. Now see here. After visiting D, there is any new there is any non-visited nodes are connected to this adjacent this D vertex. Definitely not, because of A is visited and E visited. So what to do? So whenever this is happen, we need to take a backtrack. So when there is no new vertex to be visited, then use backtracking on and pop one vertex from the stack. So what happened here? So all our visited elements we having to the D. Then what will happen? Now we need to perform the backtracking. So backtracking activity coming to the E. Okay, again we are coming to the E, which is represented in the form of pink line here. Okay, now whenever you are performing the backtracking, we need to remove a element from the stack. So which is top on the stack, which is top we having the stack that is going to be deleted now. Okay, so there is no vertex to be visited from the D. So use backtracking. So whenever using backtracking, what you have to do? Pop D from the stack because of D is on the top now. So that's why we are going to remove the remove the vertex from the stack. Then go for the step number 7. So visit any adjacent vertex of E. Okay. So what is the adjacent vertex we having here of E here? So already D is visited, and then we came to the backtracking. Now only one vertex we having that F is not visited. So now what I am doing here? Now I am going to visit the F from the E. Yes or no? Now the visitor F. So whenever you visit a new node, what you have to do? We need to store into the we need to push into the stack. Now F is pushed into the stack. Now so in step number 8. Step number 8 is what here? So visit adjacent of F. So already C is visited and E visited. So then what we have in here? Only we left G. Now G is going to be visited because of it is not visited now up to now. So this is going to be visited from the F. Okay. So visit adjacent vertex of F which is not visited G. Push into the stack. Now we are going to push G into the stack. Okay, then see here, observe carefully from here onwards. Okay, there is no vertex to be visited from G. So what you have to do? So whenever we don't have a whenever we don't have a new vertex to visit, then what you have to do? We need to perform the backtracking. So whenever you're performing the backtracking, what you have to do? We need to pop the element from the stack. So now, so from J we don't have any new nodes because new vertex because of C is visited already, F is visited. Now what we are doing here? We are going to take the backtracking. So whenever you are taking backtracking, what you have to do? We need to remove the element from the top of the stack. So here, what is the top of the stack here? G. So now G is going to be removed from the stack. So after removing the G, what is the vertex we having here? F, E, C, B, A are the vertex we having here. Then come to the next. So you are at here now. So whether we having any non-visitor vertex we are having from F? No, because of if E is visited and C is visited. Then what you have to do? We need to perform the backtracking. So how we came like that we need to go. Okay, right? So now we are moving the back. Understood? Yes. So now, so from F to E, we are going to perform the backtracking. So whenever you are doing the backtracking, what I have to do? We need to remove the element from the top of the stack. Now I'm going to remove the F from here. Right. So then come to the next step number 10. There is no vertex to be visited. There is no vertex to be visited from F. Yes or no? So here, sorry, E. F does not have yes. So now E does not having the E does not having the new visited elements. Then what will happen? So again we need to perform the backtracking from E to C. Then when you are performing the backtracking, what you have to do? We need to remove the element from the stack. Yes or no? So here we are what we are doing. We are performing the backtracking from where to where? From E to C. From E to C. So when you are performing the backtracking, then what will happen? I'm going to remove the element E from the stack. Now E element is removed from the stack, right? So then you are at here. You are at C. Now there is any new non-visited elements are there? Definitely not because of G is visited, F is visited, E is visited, and B is visited. So when you are not having new visited elements, visited vertex, then what you have to do here? We need to perform the backtracking. Now we are going to perform the backtracking. When you are doing the backtracking, we need to remove the vertex from the stack. Now C is going to be removed from the stack, right? So here the C is going to be removed from the stack. Now in the stack, what we have in here? B and A. So now, so we are at B. So is there any non-visited elements from the B? So no, already C is visited, E is visited, and A is visited. So if you're not having non new non-visited element, then what you have to do? We need to perform the backtracking. Okay. Now from B to A, we are performing the backtracking. So when you are perform the backtracking, what you have to do here? We need to We need to remove the element, remove the vertex of B because of which is top, which is because of which is top on the stack. That's why I'm going to remove the B from the stack. Now we having only one element in the stack. So there is no vertex to be visited from B. So use backtrack and go from the stack. This is completed. Next, come to here. There is no vertex. There is no new vertex to be visited from A. So use backtrack. Okay, use backtrack. Now you can observe here from A. There is no new vertex. Yes or no? Already B is visited, E is visited, D visited. So what have to do? Again here we are use the backtracking. Backtracking nothing but nothing we have it here. Just pop element, nothing but pop A from the stack. So after popping the A, the stack is empty. Whenever the stack is empty, okay, when the stack is become empty, then produce the final spanning tree. So final what is the final spanning tree here? This is the final spanning tree. So what is our aim here? What is our aim? So before that it contains loops. Okay, before that it contains loop. So by using backtracking, we removed that loop from the graph. So this is all about the what here depth first search. What is the aim of a depth first search? So what are the loops we having uh, in the graph that are going to be removed? Nothing but we are making a spanning tree. Okay, by using the depth first search travelers. Thank you. Please subscribe my channel.